guys, welcome to Learn Extra Live Grade 12 Physical Science. Guys, it's finally your turn. I know that you're excited. I know, you don't have to tell me. As long as you're focused on our Facebook page, that's www.facebook.com/learnextra. Remember, this is the platform where you guys can just speak your mind, guys, especially in asking questions. Make sure that today you are alert and alive. You are taking notes. Talking about notes, we actually have a full site, guys, with the notes that you can actually download and print or keep on your computer, anything that you want. And that site is learnextra.co.za/live. I'll put these up on the page for you guys, just so that you guys can download your notes before Phil actually starts, because it is going to be an awesome, awesome show. So make sure that you are fully there, and your notes are ready and colorful and highlighted and all the rest of it. And in front of me here, we have Simba, guys. We have these chips. They are awesome. It's such an awesome party pack. There's chips in it. There's this notebook from Simba Cheetos. There's 5 CDs. Not just one, 5. There's the Kaya CD. There's the Donald CD. There's the love songs for the month of love. There's Malik. And there's Unati. These are the prizes for the random acts of kindness, guys. Make sure that when you pay it forward, or when you do something nice for someone else, capture that on camera, post it on our events hall, and you can stand a chance to win these great prizes. And you can share them with me as well. There's also a lanyard and a pen. Thank you to Simba and Mindset for giving us those prizes, and thank you to Macmillan for sponsoring such an awesome show, guys. Thank you for joining us today. Over to you, Phil.
Thanks so much, Kat. Okay, well, Matrix, as I said, it's always great to be with you guys, and today we're going to be taking a look at some grade 11 work. So grade 11s, if you're still tuned in, stick with us. We're going to be dealing with some of your work. Just remember, grade 12s, guys, this is still examinable. We're going to be taking a look at the conservation of momentum. So when objects collide, or if they explode apart, anytime 2 objects touch or separate, momentum is going to be involved. Now, as I've been doing the last lesson, I'm going to be taking a look at some really cool toys for you guys to play around with online. So I think Kat is busy posting these wonderful links up, and I actually want you to surf over to PHET, P-H-E-T. Now, if you guys can't type out a long search address, a really quick way of getting there is to just Google those 4 letters, P-H-E-T, and it's usually the first link which comes up. So phet.colorado, so there's really cool guys at Colorado University.edu/sims. And the one which I'm going to be looking at today is called the Collision Lab. The Collision Lab is the place where we're going to be dealing with the conservation of momentum. So what I'm going to do is I'm going to surf over to that in a moment. I want you guys to get ready and have that on the computer in front of you. And this is really cool. You can copy the experiments at home. And the really nice thing about this is inside this program, you can practice until your momentum is perfect, guys. Now, I just want to lay down a couple of rules, deal with some of the terminology that we're going to be dealing with, and we're going to get right into the simulation. But before we do that, guys, let's just do a little bit of a revision on what we're talking about. So we are conserving momentum, but first of all, let's take a look at what momentum actually is. Okay, so today was, as I said over here, we're going to take a look at objects and objects that have momentum specifically. All right, there we go. And momentum is defined as the amount of motion that something has. Now that might seem a little bit confusing because we're not sure how to describe how much something is moving, except, well, I know that something with velocity has motion. But there's something else as well. If I see 2 people running towards me, one is a big person running fast and one is a small person running fast, I'm going to run away from the big person first. The reason for that is because the larger person has more motion, has more momentum behind them. So when they collide with you, they're going to tackle you over. The lighter person has less momentum and is less of a risk inside a collision. So anyone that's ever played a contact sport like rugby will know that being hit hard by a big person is a big problem because a big person very often has a large amount of momentum. And that depends on specifically the object's mass, there we go, and its velocity. We're going to deal with that as we go through. We're also going to show that momentum during collisions and explosions is conserved. There we go. That word, conserved, means to keep the same by transfer of momentum between objects. Now that sounds really technical and sounds like something that might be inside a bank or inside an accounts lesson. Guys, this is not accounts, this is science. So we're going to try and figure out, how is it possible that although these things are smashing into each other and losing all this energy, how is it possible that momentum is going to remain exactly the same as it was before the collision? Now, this was one of the questions which rattled around inside my head until I reached university, and then eventually I figured out some tricks, and I want to show you those tricks today. Okay, and then we need to find out whether collisions are elastic or not. Okay, now this word elastic, a lot of people really start to get a little bit confused because it's got a partner. I can say that something is elastic or inelastic. Now, a lot of people say, okay, it was inelastic. Does that mean that it's inelastic, or is it inelastic, not elastic? Guys, please, please, please don't do that. What I want you to do is to just take it slow, leave that right until the end. We're going to deal elastic collisions a little bit later on in the show. And then very lastly, we're going to take a look at some of these conservation momentum concepts, and we're going to solve some exam type questions. Guys, we've had a lot of questions about, well, when is Phil going to be doing some of those problems out of the notes? Today is that day, guys. Get those notes. They are on the web. They are free. And I think, Kat, have you posted them up online?
Yes, we have them online already. They are there and ready.
That is organized, ladies and gentlemen. That is organized. We've got those notes up there, guys. They are there for you to read while we're doing the show. The one thing which I've tried to do is to try to keep some of the questions on the board the same as the ones inside the notes.
Yes.
So that means that people can
nice
follow.
Answers as well.
Absolutely, guys. We're going to be guiding you through some of those questions and helping you out with those. We've also left a little bit of a challenge for you guys to solve on your own, so that once the show is done, you can work through some of those questions. Okay, so we know what we're doing today. We're going to be taking a look at momentum itself, conserving it, and then we're going to take a look at elastic or inelastic collisions. Okay, but before we get too tied down with the terminology, let's break it down into smaller pieces. Okay, so here we go. All right, well, first of all, what is momentum? Well, now momentum is signified by P. Now, this is a bit of a weird thing. Okay, I would just want to point out that P itself is a small p. It's a lowercase p. The reason that we don't use M for momentum is because M is already taken by mass. Okay, so guys, unfortunately, we're having to reach for other letters, and capital P was already taken by pressure, so momentum needed another letter. Okay, so here we go. Momentum is P. Now the question is, what are these other letters over here? Well, we've already said that momentum is the amount of motion. So there we go. The amount of motion which depends on the object's mass and velocity. So there they are, guys. I've got my mass and I've got my velocity. Now, please, guys, just remember, it's got to be in the correct units. So mass is always in kilograms when you're working in physics. Remember, it's grams for chemistry. And then velocity. Velocity is m dot to signify at times m dot s to the minus 1. So that is meters per second. Okay, now if anyone's paying some real attention, you can see that momentum is calculated using velocity. Velocity, ladies and gents, is a vector. My velocity over here is actually a vector. That means that momentum itself has direction. So I can calculate the magnitude, in other words, how much I have, and I can use the direction of momentum. Guys, just remind yourselves, please, this is the number one problem, is that momentum itself is a vector. So it has a number, which is its magnitude, and it's got direction, guys. And I can tell you, if you're having problems with momentum, I can almost guarantee you that it's direction that's haunting you. I've said this before when we talked about projectile motion. Guys, watch your positive direction. When we start a question, diagram and direction is first for any physics question. Diagram, direction. Now, a lot of grade 12 learners are telling me, sir, but we don't get any marks for my drawing, for my direction. And I say to you, well, guys, you're not going to get any marks after that if you don't do your diagram and direction, because that is a guarantee for your success. So momentum itself, just planting the idea, P is equal to mass times by velocity. So let's just go to that again. Right, so P, which is my momentum, is just mass multiplied by my velocity. Okay, well, here's the question. If I take a look at an object with momentum, the question is, how do I conserve momentum if the velocity changes? So I want you to start thinking about objects which strike each other. I've got a big ball, I've got a small ball, and they smash into each other. Let's say one is a rugby ball and one is a tennis ball. Now they change their velocity. The question is, how does the total momentum remain the same? And the answer to that question is inertia. Okay, now, sorry, not inertia, but impulse. Let's just make sure we get our terminology correct. Sorry. Impulse, I hear you say, okay, well, impulse is the way that I change the momentum of an object. So there we go. It is the change in an object's momentum due to a force acting over a time. And the way that I identify the equation over there is that I find the one which has got a change in the momentum. There's my force. Let's just signify the units. So a force acting over a time. So my change in momentum is brought about by a force and time. Now, grade 12s, remember back to last year when things collided, they exert a force on one another. The amount of time will change the amount of impulse, so how much momentum is being changed. Now, I'm not sure if we're going to get time to answer some questions on impulse in terms of collisions, in terms of car safety, but that's a very common question. Okay, so my change in momentum is equal to the force during the collision multiplied by time. But guys, please remember that force itself is measured in newtons, and it's also a vector. Time measured in seconds. Right, that's not a vector itself, but because I multiply it by force, it does make into a vector, or make a vector, which is the impulse. Okay, now you're saying if I'm getting the change in momentum of an object, how is it possible that I'm able to conserve momentum? Well, here's the trick. When I talk about impulse, I'm talking about one object at a time. Now, when an object moves, it has a certain amount of momentum. I think of impulse as the transaction between the two. When the two touch, they trade momentum. In other words, impulse is the way that momentum is traded from one object to another. They give each other momentum. So if you are stationary and you decide to get up from the TV and you run into your little sister, please don't do that.
Yeah, please.
Okay? All right, so if this happens, you're going to be giving her a little bit of momentum of yourself. So what's going to be happening? I'm going to be losing momentum, but she'll be gaining momentum. So when two objects collide, they trade momentum. The amount of momentum which they exchange is called the impulse. This is because there's a force, and this is why your head is hurting after running into your sister, and this is why she's screaming at you. And that's a very short collision, and that's why it hurts so much. Okay, so just once again, impulse is how much the momentum changes during a collision. Now, there's one other thing which I just want to start highlighting. I want you to start thinking, how does the total remain the same? And this is actually the key. That if a certain amount is given to the other object, it is still in those two objects. When I start to take a look at a conservation momentum, I need to talk about something called the system, which is the collection of objects inside your particular example. So what we're going to start doing is I'm just going to plant the seed before we take a break. So what does it mean to conserve this momentum? Now, guys, this is the textbook definition. I'm just going to show you some of the key words which your examiners are looking for. Okay, now you'll see several different definitions of this, and I'm going to highlight them for you. Okay, so I see the total linear momentum. Guys, that means that we're dealing with a straight line, and we're dealing with the total specifically, the total linear momentum of the system. Guys, please, the system talks about more than one object, will remain the same in an isolated system. Okay, so now I've mentioned the word system twice there. Now, what's very important is that this word isolated is there. Now, guys, you've all felt isolated. Isolated means to be away from other things and from other objects and people. Isolated means that there's no other objects or forces involved. So the objects are alone. Now, that's not the correct scientific term for it, but I just want to get the idea into your heads before we jump into all these terms and all this terminology. So the total linear momentum of the system will remain the same. And guys, there it is. There's the money. Remain the same. That means conserve. So if I conserve something, if I look afterwards, if I look before, I will have the same amount. I want you guys to stew about this and to think about this and to start thinking, okay, well, am I going to run into my sister or not? What do you think,
I
Kat? Should they?
don't think people should be running into their little
Okay,
sisters.
so no running into the family
No running
members.
into little sisters. But you can maybe just put them on the couch next to you and tell them to sit there quietly while you watch your show. We'll see you right after the break, guys. Welcome back, guys. Of course, I am loving the questions that are coming in right now. You guys are really on the ball, and I know that you really want to do well. Keep them coming, guys. If there's anything that you don't understand, anything that you want clarification on, Phil is here. I know he's one of your favorite teachers, so make sure that you are in sync with him and you've printed out those notes or you've got those notes on tab so that when you have, when he's asking a question on here, you're just like, I have the question right there and I can actually refer back to it. So that later on, when you are writing exams or are studying for those exams, you can actually just flip back on those notes and check them out all over again. Isn't that right, Phil?
Absolutely, Kat. Guys, it's all about you guys, and I love to see the sharing on the page. Most of the times, I don't even have a chance to answer the questions because somebody else has jumped right in there, right?
Exactly, which is great.
Okay, well, guys, that's what it's about. It's about sharing. It's about community. I want you guys to help each other. Later on at night, sometimes I go on there and I help you out with some of your questions. But today, I saw some of the questions about impulse. I just wanted to clarify something before we moved on. Somebody was asking, what is the difference between impulse and momentum? Okay, well, again, we said that momentum was how much movement an object had. Impulse is how much that value changes. So if I've got 5 kilogram meters per second, which is how we measure momentum, and it reduces down to 2 kilogram meters per second, can you see that the momentum has decreased? It's decreased by a value of 3 kilogram meters per second. That is the impulse. It would be -3 to go from 5 to 2. So impulse is how much your momentum changes. There's only one major difference in terms of the units. Impulse is usually measured in Newton seconds. Now, the reason that I measure it in Newton seconds is because of its equation, force times time. So the force in the collision over there and the time over there, the reason that those two multiply together is to give me those Newton seconds, so the force for a certain amount of time. Okay, now before we went away on the break, I showed you that impulse is what happens when objects change momentum. They give each other momentum. Now, I just wanted you to think about this whole idea of the conservation momentum principle. So we started talking about an isolated system. We started talking about the total linear momentum in a system. Now, a lot of you are saying, okay, well, these are words which I don't use every day, so let's just try and unpack it a bit. This word system means a collection of objects. So it's more than one thing. I usually talk about multiple objects as a system. Now, when I start to talk about things being conserved, they remain the same. And we had some questions about the word isolated. Isolated means that these objects are alone. That means that they're not interacting with any other objects. There's no other forces accelerating them or decelerating them. They are isolated. Guys, an isolated system is the only one where momentum remains the same. You'd be surprised how many isolated systems you can talk about. A very nice example of an isolated system would be 2 snooker balls on a table. And this is where we're going to start to take a look at our simulation. So if you guys were looking for that FET simulation, I want you to start gearing yourselves up. In about 5 minutes, I'm going to be jumping over to that really cool animation. And there's a fun game that you can play. So let's start taking a look at a very simple situation. There's 2 trolleys. They're headed for each other. I just want to draw your attention to the diagram. So what I'm going to do now is I'm going to highlight the various motion of these objects. Okay, so I've got object M1 on the left. The reason that I use M1 is because that's my first mass. It has a mass in kilograms. It is heading with VI1, which means the initial velocity of that first object. The other object, M2, is headed towards it with its own velocity, so VI2. Now, they both have their own momentum. Now, something you'll get quite used to in conserving all of these is that I'm going to have 2 diagrams. I'm going to have what happened before the collision, and I'm going to have what happened after the collision. Those 2 must be very clear pictures. So I've shown you what was happening before. And when I push 2 trolleys closer together, you know exactly what's going to happen. These 2 trolleys are going to collide. The minute I see a collision, I know, this must be to do with momentum or impulse. But when I take a look at them as a collection, now a lot of grade 12s are saying, well, should I use impulse calculations? Should I use conservation calculations? Guys, you can use both. It depends on the question. If I'm asked to conserve momentum, I look at the whole system. The system is M1 and M2 all together. M1 and M2 together make a system. So there we go. So M1 and M2, that is my system. These two objects make up my system. The reason that I put them on these nice blue wheels is because that allows them a frictionless environment. They're going to slide right along until they strike each other. Let's see what happened after the collision. Now, if they're exactly the same size and they just bounce off each other and they separate, let's take a look at what happens over here. I still have M1, I still have M2, but look at what they're doing. The final velocity of the first object is now away. It's changed its velocity. What about the other one, VF2? It's also changed its velocity. So they came in, before they were headed towards each other, then afterwards they were headed away from each other. Most of you have done this before with a toy car. So two cars headed towards each other, you push them and they strike each other and bounce off again. Now this is quite hard to visualize without starting to take a look at one of those animations, and that's exactly what we're going to do in a moment. But before we do, I want to show you how to apply the principle. Let's see what it actually means in an equation. Then we're going to start playing around with the fun stuff. So if I've been given a situation of before and after, here's the trick, grade 11s. Sorry, I say grade 11s because this is grade 11 work. Grade 12s, this is for you. Now, when I try to conserve the momentum, I need to have a momentum term for each individual object. M times V is momentum. So what I'm going to do is when I start to conserve this, my first step is always to state the conservation of linear momentum. The P initially is equal to the P final. That means that the momentum initial equals momentum final. I didn't lose any. The total amounts are going to remain the same. Now, lots of you at home are going, I don't really believe you, because the velocity's changed and velocity makes momentum. And how is it possible that if the velocities change, the momentum doesn't change? Guys, have faith. We're going to take a look at it in a moment. Now, how do I apply this? I want you to see that when I write out this full equation, this one is not given to you, but it's a lot easier than you think. What I'm going to do is I'm going to run through and highlight the important pieces of information. Okay, so follow the yellow pen. What we're going to be doing now is we're going to be taking a look at the first object's mass and its velocity. If I multiply those two together, I get the first momentum. So that is the initial momentum of that M1. So M1 times its initial velocity will get me a momentum. Each separate object needs to be treated separately. So again, M2 is currently separate. That means that it's away from the other object. So M2 over there, with its initial velocity, will go and get me the other initial momentum. So I had two objects, I had two momenta. Guys, this is how you figure out this equation. M times V gives me momentum. So for every object I see, I need to say M times V for every object. So here we go, M times V, M times V. We did it twice because there's two objects. What about afterwards? What we're going to find is exactly the same thing. So for final, let's follow the yellow pen. There we go. I've got M1, I've got VF1, the final velocity one. There is the momentum, guys. It's right in front of you. So M times V again. What about the last one? M2, VF2. There's my last momentum. Okay, well, this is starting to get a little bit mathsy, and I'm starting to itch to play with some experiments. So what I'm going to do is I'm going to ask you to go through to that PhET simulation. Now, that PhET simulation I've already got loaded up. It's called Collision Lab. I'm going to show you a little bit about Collision Lab, and we're going to try and see what's going on inside here. Now, I've already set up the program. I just want to show you some of the shortcuts inside the program, which might make your life a little bit easier. So what I've decided to do is I've decided to show the velocity vectors. So what I'm showing you over here with the cursor is that I can show the velocity or not. So you can actually change this. So back onto here, I've told my particular experiment, that I would like to have the kinetic energy of the system. Now, before we get too confused about that, we're going to take it away for now because I want to show you some other cool stuff on here. Now, the really nice thing about this is you can use your mouse to actually drag these objects around. You can change their mass, you can change their velocity. And then what you can do is you can let the system happen, or you can let the system work. Now, before we do that, I want to draw your attention to this little slider bar on the right here. I see some words over here. It goes elastic to inelastic, and I can change this value quite a bit. I can go from a maximum of 100% down to a minimum of 0%. We'll explain the meaning of that in a moment. But for the moment, I just want you to set that at around about 50%. So there we go, 50%. We're going to leave it right there. Now what we're going to do is we're going to do a collision. We're going to collide two objects. Now the really cool thing about this is you can tell exactly how much of the velocity and the mass and everything you've got. You can see all the numbers in front of you. So I've got object 1, which is a red snooker ball over here. Then it approaches a larger green snooker ball. Now, what I can do is I can start to drag and change the velocity. What I want you to notice, and this is something that we haven't talked about a lot, is I haven't talked about this number at the bottom here, this momentum, having a sign. Guys, this tells me direction. What I want to emphasize and what I want to just drive home is that I'm going to give this object some momentum in the one direction, and I'm going to give this object some momentum in the opposite direction. Guys, direction is everything. So what I've done is I've given object 1 a momentum of a half a kilogram meter per second. So I'm actually going to draw on here. What I'm going to do is I'm going to make some notes on here, and we are going to attempt to follow each other. Okay, so there we go. I'm going to be dealing with momentum on the left-hand side. Let me actually try see if I can change that color slightly over there. All right, so I'm going to be dealing with a momentum over there, and I'm going to be dealing with this momentum over there. I want you to notice that those two are the momenta before I've let the system work. The red object had a momentum of 0.5, but it's positive. The green object has got a momentum of -1. Now, I want you to note that the green object is much, much heavier. It's got a bigger mass. It has a mass of 1.5. The smaller object has got a mass of a half. Now let's see if momentum is conserved. I'm going to let these balls smash into each other and collide. I want you to follow these numbers. So at the moment, I know that momentum of object 1 over here, let's write it out. Momentum 1 of my object here is a half. Momentum 2 at the moment is -1. So I want you to get out your calculator and find me the total. Actually, you should be able to do this inside your brain. So what is the total of positive a half and -1? I know that the momentum before the collision at the moment is -1/2. So let's allow the collision to happen and see if the total is exactly the same. So just a reminder that at the moment, initially, I've got -1/2 kilogram meter per second. Let's see what my momentum will be once I've allowed these two objects to collide with each other. So let's take this away. Right? Let's take all the ink away. Let's let the magic happen. You know what's going to happen. These two velocities are going to allow these objects to collide. So when I push play and I allow them to collide, something really weird has happened. All of a sudden, these objects are moving at very different velocities. And we're going to do that again. Guys, I want you to watch what happens to their momenta. The momentum of ball 1 was initially a half this way, and now it's 0.44 in that direction. It's changed its momentum. How is it possible that my teacher is telling me that momentum was conserved? Well, guys, the change in momentum of a single object, it's called its impulse. If I look at the whole system again, let's do some magic over here. So let's just reset this. Let's go back to our original values, and let's push play. Guys, if you take a look at the total of their momentum at the moment, if I add -0.44 and -0.06, what I'll find is still exactly the same total. Guys, you can set this up, you can play around with your masses, you can play around with your velocities. So while you're busy playing around with those, guys, I think it's time for a breather. What do you think,
I
Kat?
think so too. I think that you guys actually need to press reset because that thing looks awesome, Phil. I must admit, people are actually enjoying the way you're actually doing this. It's really awesome.
Oh, very nice.
It's really awesome. So guys, you deserve a break. We'll see you right after this. Welcome back, Mindsetters. I hope that you guys are really, really enjoying this show, and I hope that it's really benefiting you and that you're actually concentrating. It's really important that you guys are concentrating, both grade 11 and grade 12, because this will really help you. It's a really big section, and it's a really nice section. Most of you are saying how this is actually your favorite section. So I hope that you guys can jump onto the page and help other people. If you're just watching and you know what's going on, please, please help other people. They really are wanting your help. People have said, hey guys, let's keep helping each other or answering each other's questions or anything. Or you guys can even meet up on the page and just chat to each other, make friends. And yeah, it will be a really special and easy year if you do that. Over to you, Phil.
Thanks so much, Kat. As she said, guys, meet and greet online and help each other out. What I'm going to do is I just want to go through this experiment again and just show you what was actually going on. Before the break, I showed you two balls which were heading at each other. The smaller one, the 0.5 kilogram object over here, let's actually draw it around. I've got a 0.5 kilogram object over here. And this is before the collision is taking place. So I want you to become very, very good at deciding what's going on there. So I've got a 0.5 kilogram ball over there. It's got an initial velocity of 1.0 meters per second. There we go. That gives me a momentum. So if I multiply m times v, that gives me a momentum of 0.5 kilogram meters per second. Now that seems like quite a mouthful. But once we let the animation play, it will actually make a lot more sense. Okay. Now, the one thing which I did always tell you is to indicate a positive direction on my example. So I've said that towards the right on the screen is my positive direction. So that means the velocity which belongs to the second ball of mass 1.5 kilograms, take a look at that, 1.5 kilograms is going to be at a negative velocity. So there we go. My negative velocity over there is negative 0.67. Guys, please, this is where the direction comes in. That velocity is negative, and it means that the momentum of this object came out to be negative 1, if I calculated all of them together. Negative 1.0 kilogram meters per second. Okay, so just before the break, what I showed you was what happened before, initially. So let's grab our calculator. Let's figure out how much total momentum I've got. So this really nice calculator, what we're going to do is we're going to add together the initial momentum. So the object on the left, ball number 1, has got a momentum of 0.5 kilogram meters per second, plus the momentum of the second object. Now that's negative. I always put brackets to show a negative. So there we go. So the negative button over there will tell me that I've got a negative value. So negative 1 or 1.00. Now what that's going to allow me to do is to find the total momentum before the collision. And I want it always in decimal. So it's minus or half. Now what I did was I allowed the simulation to take place. So I said play. And what's going to happen, and I'm going to ask my producer to put this up on your screens as well, is these balls are going to strike each other and then they're going to go apart again. So when I push play, they collide and they go off with their own separate momenta. Now let's just figure out how much momentum is each one has got. So there we go. My momentum over there is negative 0.44 kilogram meters per second. My momentum over there is now negative 0.06. Guys, if you're quick with maths, you'll realize that if I add these two numbers together, wait a minute, something's going on. I've got exactly the same momentum as I did before. I've got negative a half. the momentum before the collision is the same as the momentum after the collision, even though they changed velocities. Guys, it doesn't matter that they might have lost energy or whatever might be the case. The total momentum before is the same as the total momentum afterwards. Guys, I want you to get in there, play around with the mass, play around with the velocities, add up the momentum before, add up the momentum afterwards. It's always going to be the same. Now, one other thing which I want you to play around with when you've got a little bit of time is to play around with the elasticity. That's quite fun. Okay, but before we get too carried away, let's get back to our presentation here. Let's try and figure out what's going to happen if these two objects don't separate. Now, what I said to you guys was that momentum is always conserved. And every time I've got a momentum, an m times a v, that means that I've got a momentum. So in our second example, before the collision, I had exactly the same situation. I had mass 1 headed towards mass 2 with its initial velocity. So here's mass 2. Mass 2 again has got its initial velocity. So I've got two objects, two momentum, or two momenta. What that means is that when I conserve momentum, I'm going to have m1 times v initial 1, m2 times v initial 2. I need to have two separate terms in the maths. Now here's where the trick comes in. After the collision, they move together. So m1 and m2 move off together with one single final velocity over there. Okay, so let's try and figure out what the equation might look like. Okay, so let's do exactly that. So I always start off with P initial equals P final, but take note, this is slightly different to the last one. Let's just highlight the differences. So still I had M1 times V initial 1. There it is. There's my first term. My second object as well. I've got M2 V initial 2. There it is. But now, after the collision, there's only one object. So that means that the masses must add to each other. They have become one. And that's what's going to happen inside our example that we're going to look at. They head off with one single velocity. If we get a little bit of time later on, I'll explain and I'll show you inside the animation. If you guys click right down on the elasticity, you'll actually see that the objects stick together if you're still playing around in that PhET program. Okay, but what about the last situation that you can find? And this is called an explosion sometimes. Let's just go back there. All right, what happens if these two, instead of going together and sticking together, what would happen if they headed apart from each other? Now, some of you might have asked, how do I do this? Well, guys, it's actually really easy, and we don't need to draw out a separate slide. What I do need you to do is to just reverse this around. What do I mean? Now, I know that this is not going to make much sense unless I actually draw this out. So instead of having our objects separately in the beginning, I've got them joined on together. So I've got my two objects. They are now joined together for some or other reason. They might be tied to each other. And what happens is an explosion takes place in between them. So once again, I've got M1 and M2. I want you guys to predict what is happening. So after the collision, what I'm finding is that my two objects are now headed away from each other. So an explosion happened between them, and they are headed away from each other. So M1 and M2 were together, and now they are apart. Guys, I just want to show you how easy this is in your exams. So let's say I was given an example where M1 and M2, the two objects, were together initially. Draw in your positive direction. Here is my initial, so my before. So this is what I want you guys doing at home. So before and after. This is the very last example of what is going on. Before and after. Now let's just make some sort of assumption. So before, these two objects might have been moving with some sort of initial velocity. We're not sure. That might be 0 if they're stationary. But every separate object needs an m times v. But because they're not separate, they're going to be working together. So m1 plus m2 times by one initial velocity. Notice how they're together. What about after the collision? Well, m1 now has its own v final. So v final 1 plus m2 v final 2. Guys, it's exactly the opposite of the previous question. Okay, now, before we get too carried away, I wanted to introduce that idea of an elastic collision, okay? And this is the confusion thing. When I start to talk about inelastic or elastic, and then I start to say in elastic collisions, it's quite confusing. So what I'm going to say, is the collision elastic or is it not elastic? Inelastic is a horrible word. Now, let's take a look. Is the collision elastic? Okay, well, there's a few steps, and this is actually quite easy. Cool thing about that demonstration that I showed you on the board is it actually tells you immediately. But this is what you got to do in the exam. First, I've got to calculate the total kinetic energy before the collision. Then I've got to do it again after the collision. You're saying, okay, well, Phil, I'm doing the momentum before and after. This sounds awfully the same. Guys, when we're looking at elastic, we're taking a look at energy. Guys, not momentum. Now we switched gears. We're starting to talk about kinetic energy, which is something else, which is a property of moving objects. Now that means that any moving object has got kinetic energy. We want to see if the total amount is still there. Okay, so here's my step. Calculate the total amount before, calculate the total amount after. Now we want to see if they match. In other words, is the kinetic energy the same as it was before the collision? Are they the same? Now, what does it mean if they are the same? If they are the same, I say that the collision is elastic. Okay, so an elastic collision is one where the energy, or specifically the kinetic energy, is going to stay exactly the same. Now let's go back to our demonstration over there. Collision lab is ready. So collision lab over here, what I want to do is I want to click on this piece that shows the kinetic energy. So over here, we can see this box over there, and now we can actually see the kinetic energy. So let's go back to our equation right at the beginning. At the moment, before the collision takes place, I want to see where the collision, or how much kinetic energy there it is. I've got 0.58 joules before the collision. Now what I'm going to do is I'm going to let the collision happen, and we're going to see what happens to that collision. The kinetic energy inside that collision. So let's let the collision happen. There we go. I push play. What I notice is that my kinetic energy has decreased. This is not an elastic collision. That means that the kinetic energy of these two objects together has decreased. This is not an elastic collision, guys. Okay, so I hope that that's clear. One of the things that we can actually do inside this program is we're going to start playing around with how elastic collisions are. So let's just do that quickly. So let's take away all our pens. Let's increase the elasticity to 100%. Now this is going to change all the values, but something quite cool is going to happen. I've got 0.58 joules before the collision. If it's 100% elastic, what's going to happen is after the collision, I will still have 0.58 joules. That was an elastic collision. So if I start taking a look at that value over there, the kinetic energy of an elastic collision does not change. So kinetic energy during an elastic collision will not change. Guys, please don't get momentum and kinetic energy mixed. I know there's M's and there's V's and it's all kind of confusing. Okay, I only start to take a look at kinetic energy when I'm asked to, when I'm told to, or when we're starting to take a look at elastic versus inelastic. Okay, again, I don't like that word. So not elastic is a better way to say it. Okay, now before we get too confused and we get too sidetracked, let's actually get into a past paper question. Guys, this is inside your notes. This is from a Department of Education exam. It's in the March 2011 paper 1, and I love it because it's a great example of what we've been doing. We've got two shopping trolleys, X and Y. So there they are. We've got these two shopping trolleys, X and Y, and they're both moving to the right along the same straight line. The mass of trolley Y is 12 kilograms, and its kinetic energy is 37.5. So what I'm going to do is just make sure that everyone can see this data. So there we go. We've got an amount of kinetic energy. What about its mass? 12 kilograms. And we know that we're talking about trolley Y. And just a reminder, we've got both of these objects. So trolley X and trolley Y. We've got to be able to calculate the speed of trolley Y. So let's concentrate on the information about trolley Y. So there we go. Let's concentrate on that guy. Trolley Y, we've got a mass, we've got a kinetic energy. Guys, you don't need a diagram in the direction for this one. Please, this is just a straightforward solution. So calculate the speed of trolley Y. Now, I only know of one equation which has got a mass and a kinetic energy. And guys, that is K is equal to a half mv squared. Now, this was a nice, easy way to start this question. But the cool thing about this is this brings in energy. And guys, if you're watching and you're starting to take a look at energy and power and work, guys, next week we're going to be revising that. So stay close. So how do I go about solving this? Well, I state my equation all the time. Every single time I'm going to state the equation. So my kinetic energy is equal to half times m times the velocity squared. Let's substitute. There we go. So I've now substituted in my kinetic energy. I've substituted the mass of trolley Y. Now all that's remaining is my V and my V squared. Now, I'm not going to go through all the steps. I'm just going to leave it as 2.5 meters per second. Now, a lot of you are saying, Phil, what about the direction? Why don't you give us a direction? Well, read the question carefully. It says calculate the speed. There we go. Guys, the speed itself is not a vector. So if I take away the direction from velocity, what I'm left with is speed. So when they say the speed, all I have to give that. Or another way that they could ask you is calculate the magnitude. Now, we've had some questions about that word. The magnitude of the velocity. That means how much velocity. So magnitude just means the size, guys. Anytime you see the word magnitude, please don't be afraid. It's not a word that I use in every day. I don't say, please put a large magnitude of sugar in my coffee. Okay, people are going to look at me funny.
Yeah, no, I think they will.
Okay, but I'd still be correct. I should say, well, you know, what magnitude of coffee should, how much should I put in there is what I should be saying. So how much sugar? Magnitude is just another way of saying how much. Okay. So I'm hoping that when I look at the magnitude of your marks at the end of the year, they're going to be way up here. So guys, keep watching, and we're going to make sure that happens. Okay, so calculate the speed of the trolley Y. Now, there's a second part of the question, and this is where the momentum comes in. So it says that trolley X now enter the second object. Take a look at the amazing diagram, which they've been given. There we go. So I've got trolley X, and trolley X itself is appearing on the left-hand side. There it is. So trolley X is headed in. It's got a mass of 30 kilograms. I like to draw in the information on the diagram. Guys, I'd like you to do the same. It's a great way to organize your information. So 30 kilograms of trolley X, just a reminder that trolley Y is 12 kilograms. It collides with trolley Y. Ding, I immediately know that a collision is conservation of momentum. So there we go. Trolley Y is now involved. And they stick together on impact. So there we go. We've got X and Y all together. They are now stuck together, so now I have 30 and 12 kilograms moving together with one velocity. Okay, so after the collision, the combined speed of the trolleys is 3.2 meters per second. Unfortunately, that should be a little bit bigger, guys. I'm pretty sure you can't read that. So meters per second, ignore the effects of friction. That means that our system is an isolated system. There's no outside force. There's no outside object. So there we go. Calculate the speed of trolley X before the collision. So guys, what they're looking for is how fast trolley X was traveling in here. So V initial of object number 1. We've already got V initial of object 2, and we've got some other information. We know what V final is. Guys, again, I've marked the positive direction. Please make sure that you do exactly the same. Okay, how do I go about this? Well, I've got a situation of before and after. So let's take a look at how I'm going to start solving this. Well, I've got to calculate the speed of trolley X before the collision. That's what I'm after. I'm after one of those velocities. So when I start to solve this, P initial equals P final. Okay, that's the way that I always start with one of these questions. They actually give you a mark for stating the conservation momentum principle. Guys, that's marks for free. Okay, so now when I start to expand, sure, guys, now you've got to pay attention. I've got two objects before. There they are. Object number 1, there's my trolley X. There's object 2, trolley Y. So I can see that mass, so let's just highlight it as we go. So mass 1 times velocity initial 1. So that's object number 1 already sorted. So there we go. We've got that first object, which is now sorted. What about the second object? its mass times by its initial velocity. There we go. Second object sorted. What about the combined set of trolleys? There we go. Their masses are now added together and they move with one final velocity. So I've got this final velocity. There we go. We've sorted out all the objects inside all of this. I've got my momentum before. I've got my momentum afterwards. Let's put in some numbers and let's see what happens. So if I take a look at this, there we go. There's my solution. I've substituted in my trolley 1, my x mass, my y mass, my y initial. There we go. There's a combined, and there's the final velocity. Guys, if you go in and solve for VI, that's all that's left. And if you guys are getting the same solution as me, there we go, 3.48. Now, what I've decided to do is just to put in the direction just to be safe, although they asked me for the speed. So all I would need is actually the magnitude, and there it is, 3.48 meters per second. It's in the original direction of motion because I found that it was a positive number. Guys, signs are everything. I think we've got time to squeeze in one tiny short question just to finish this off. And this deals with the impulse in this situation. It says, during the collision, trolley X exerts a force on trolley Y. The collision time is 0.2 seconds. There's the sign that I might be starting to talk about impulse. It says, calculate the magnitude of the force that trolley X exerts on trolley Y. Now, what we're going to do is we're going to focus our attention on trolley Y and what is happening to it. So just quickly, what I want to emphasize is that I'm going to say, okay, well, here's the equation which I get off my equation sheet. I want you to notice that that is the equation for impulse, and impulse is actually the change in momentum. So m times vf times minus m times vi, that is momentum final minus momentum initial. Remember that we're dealing with trolley number y. Okay, so what we're going to do now is substitute the values. My force multiplied by the time of impact, there's my mass, my final velocity, my mass, my initial velocity. This was before the impact. And what I'll find is that I can calculate my force. My force is 42 newtons in the original direction of motion. That's how hard trolley X struck trolley Y at. Guys, I know it was quite quick. I want to see if you can play around with that FET animation and deal with some of the impulse yourself. Guys, I've really enjoyed this lesson. But now, I just wanted to answer a quick question you had.
Sure.
Do you mind?
Let's answer one quickly.
Okay.
Okay, so there's some that you've answered for. You've answered a lot of them. But there's just this airbag one that Chifiwa has been wondering about all lesson. So
very
maybe
nice.
Just quickly, just in a...
Cool. Okay. Guys, a lot of you have seen a question about airbags and how they work. And the answer lies in impulse. Now, let me just remind you that impulse is your change in momentum. And that's equal to the force times by the impulse, the time of impact. Now, what I'm going to show you now is that force, if you rearrange it, is equal to your change in momentum over your change in time. The larger the change in time, the less the force. They are inversely proportional. If I increase the time, I will decrease the force. And that's what an airbag does. It comes out to meet you and increases the time of the impact. So it decreases the force. So that's why airbags keep you safe.
Okay, awesome. Thank you very much, Phil. And thank you guys for tuning in. I know that you guys are so proud because all of your questions have been answered. And you guys are happily on your way to those A's that we've been chatting about. So good luck for those of you who are writing tests this week, which is most of you. Have fun, guys. Relax. And remember to learn more, learn extra. And same time, same place next week. Thank you to Macmillan for sponsoring such an awesome show. Cheers, guys. Bye.